Good morning, everyone, and welcome to EDP and Applied Mathematica Seminar. It's a pleasure for me to open session 29 of this seminar. Today we have two excellent speakers, Emmanuel Trelat and Julia Petrova. Introducing Emmanuel Trelat, we have Professor Diego Souza. Thank you, Diego. You can start.
Okay, thank you, Juan. It's a great pleasure to introduce Professor Emmanuel Trelat from the Laboratoire Jacques Lyon in Paris. Professor Trelat is a well-known mathematician, and he received many prizes. Just to say a couple of them, he received the Prix Blaise Pascal, the Felix Klein Prize, and now he's the director of Laboratoire Jacques Lyon. So, the title of his talk is Turnpike and Dissipative in Optimal Control. Thank you, welcome, and the word is with yours.
Thank you very much. Thank you very much, Diego and Juan, for your invitation and for this very kind introduction. So I'm very, very glad to talk about a series of works that we have done with my PhD student, Gontran Lance, with my former postdoc, Zhan Zhang, who is an assistant professor in Wuhan in China, and Enrique Zoisois, who is now a professor in Erlangen in Germany. And our works are about the turnpike property in optimal control. So let me explain first in very simple words, what is the turnpike property in optimal control? So, I switched on slide number 2. Can you just confirm me that the switch was working?
Yes, it works, yes.
Thank you very much, Diego. So it is this property that you can observe, you know, when you are going to Google Maps, for instance. If you would like to go by car from an initial point, like if you are starting from Orléans, which is my town in France, and you want to go by car to the Chambord Castle, you know, this very, very famous castle, one of the most beautiful on earth, which is quite close to my house, by the way. And you would like to go there by car, let's say by minimizing the time or by minimizing the fuel consumption or something like that. So, of course, you are going to Google Maps, and Google Maps gives you several ways in order to bring you from the initial point that is there to the final point that is there. You can see the several ways to go there. And actually, what Google Maps says is that the best possible way in terms of minimizing time, say, is to reach as soon as possible the highway, which is what you can see here, A10. A10 is the name of the highway. It's a highway that is going close to Orléans. And so as soon as possible, your car should reach the highway. That is the turnpike, precisely. The turnpike is actually the English name for highway. And then you will follow the highway, the turnpike. So in some sense, nothing much interesting will happen there during the time you are along the turnpike. It's a kind of steady state in some sense. Nothing happens. And at some point, you will leave the highway and try to reach, as you can, the final point. So this is the typical picture that you can keep in mind of what is the turnpike phenomenon. So let me now explain in more mathematical words. Actually, the turnpike property stipulates that, it is written here, that if you look at the solution of an optimal control problem in sufficiently large time, then you expect that this solution, this optimal solution, should spend most of its time near a steady state. So near the Turnpike set, as I will explain in one moment. And actually, this property was postulated by the famous Nobel Prize Samuelson quite long time ago in 58, and it was in a context of econometry. And actually, I can show you, because it is funny, I can show you the proof in quotes by Samuelson, which is written here in green. So you can read the proof, but I will explain it on the picture. It says that if you are going by car from an initial point to some final point, then if the initial point and the final point are sufficiently far one from each other, then certainly it is more economic, it is more optimal to reach the turnpike, the highway, than to follow the highway during a long time, and then at some point leave the turnpike and steer your system, your car, to the final point. In contrast, imagine that you make only a local move. Imagine that the final point is in the neighborhood of the initial point. Then in that case, of course, the optimal solution does not go to the turnpike. It makes no sense. The optimal trajectory is purely local. It would make no sense to go to the turnpike, go along the turnpike and come back. It would not be optimal. So this is exactly what Samuelson stipulated and postulated quite a long time ago by saying that if the time horizon in the optimal control problem is sufficiently large, then you expect that in some sense, the optimal solution will spend most of its time near something which is like a steady state. So, well, let me ignore the bibliography on that subject, which is quite numerous. But let me directly come to the mathematical framework. So, throughout the talk, let us consider a classical control system given in the form of x dot equal to f of x and u, where x is the state. It can be infinite or in infinite dimension, it does not matter. U is the control. You put some constraints on the initial and the final point, and you would like to minimize some cost criterion. So this is the typical formulation of a general optimal control problem. And the only assumption that I do for the moment is the fact that the time capital T is large. So let me give on this slide the intuition why you can expect the Turnpike phenomenon. This is just because since the time capital T is large, so let us look at the optimal control problem, which is here on the left. You can reparameterize the time by capital T. And you can set, let's say, S equal small t divided by capital T, so that epsilon equal to 1 over capital T is a small parameter. Now, if you reparameterize the time by this very simple change of variable, you reduce your optimal control problem to that optimal control problem written on the right of my slide. That is, you minimize some cost criterion, which is an integral over the interval 0, 1. But now, because of this change of variable, there is an epsilon in front of the new time derivative. Epsilon x prime of S is equal to F. And so this is why you can expect that when capital T is very large, meaning that epsilon is very small, this is as if this quantity were to be equal to 0 or almost equal to 0. So this is why you do expect that when epsilon tends to 0, there should be some convergence in some sense. So maybe some gamma convergence to the problem where the time dependence disappears completely, and finally you minimize f0 of x and u subject to f of x and u is equal to 0, which is a static optimization problem. The time has disappeared. And so this is why we do expect that when capital T is large, the optimal solution spends most of its time near a steady state, and this steady state is expected to be exactly the solution, the optimal solution of that static optimization problem. So this is the main idea of the Turnpike phenomenon. And indeed, so let me show how to derive such a property. So on the left of my slide, you have the dynamical optimal control problem, okay? And on the right of my slide, you have the static version of the optimal control problem, meaning you minimize the instantaneous cost subject to be an equilibrium point of the dynamics. In both cases, let me assume that there is an optimal solution. On the left, I will denote the optimal solution with an index capital T, because it depends on capital T, of course. And on the right, I will denote the optimal solution when it exists with a bar, like that. So for the needs of the talk, let me assume that optimal solutions do exist. Let me also assume, just to simplify, that they are unique. It is not a problem anyway. Now, in order to compute those optimal solutions, let us apply first order optimality condition. So on the left, we will apply the famous Pontryagin maximum principle in order to characterize optimal solutions. And on the right, we will apply the Lagrange multiplier rule, the KKT rule, Karush-Güntuker. In both cases, also to simplify, let me assume that there is no abnormal solution. So let me assume that all solutions are normal. Now, on the left, the Pontryagin maximum principle states that there is an adjoint vector depending on time, so that every optimal solution should be the solution of an Hamiltonian system written here, okay? And on the right, the Lagrange multiplier rule, which is written here in the Hamiltonian form. Here, what you can see below my slide is the Hamiltonian of the optimal control problem. And I just wrote on the right the Lagrange multiplier rule in the Hamiltonian form, so that what you can observe immediately is that if you look at the triple, the optimal triple, x bar, lambda bar, u bar, you can see immediately that this triple is exactly an equilibrium point of the Pontryagin equations that are written here. And it is important. So what I say at that step is that the optimal steady state of the static optimal control problem is an equilibrium point of the first order optimality system for the dynamical optimal control problem. Okay, so now I am in a position to state the theorem that we have proved with Enrique Zoisois in 2015, first in finite dimension and then in infinite dimension, also with Zhang 3 years later. And mainly what we have proved is that under very general assumptions that I can comment later if you wish, but these are generic assumptions in some sense, we have proved an estimate which measures the discrepancy between the optimal dynamical trajectory, x of t, but also the adjoint, lambda of t, but also the control, u of t, and the steady state value, x bar, lambda bar, u bar. And we have proved that this discrepancy is always bounded above with some constant by the sum of two exponentials in time. And what you can see with the sum of these two exponentials is that as soon as the time small t is positive, that is not exactly near zero, and less than capital T, that is, as soon as you are in the middle of the time interval, then the sum of these two exponentials is exponentially small. So it means that except around t equals 0 and t equals capital T, the discrepancy between the optimal trajectory and the optimal steady state is exponentially small. Let me stress that this inequality says nothing if you take small t equal 0 or small t equal capital T. But as soon as small t is very in between 0 and capital T, then this quantity is very, very small, exponentially small. So this is exactly, this reflects exactly what we wanted to prove, that is the Turnpike property. It says that the optimal solution, which is a triple now, because there is the state, the co-state, a joint vector, and the control, is approximately made of three pieces. Essentially, along the middle of the time interval, essentially it is almost stationary, with an exponentially small error. So except at the beginning and at the end of the trajectory is essentially a steady state. This is exactly the Turnpike theory. Now, this theorem gives you a statement when the Turnpike set is a singleton, is a point. But actually, it is not very difficult to extend such a theorem to what we can call periodic Turnpike, where the equilibrium point may be replaced, for instance, with a periodic trajectory, like in mathematical biology. Imagine in mathematical biology, you know, there are many phenomena that are periodic, like a heart that is beating. Imagine that you are running or doing something like that. So you are going from one initial point to one final point, which is very far away. So maybe at the beginning, your heart is not beating so quickly, but along the path, which is essentially, for instance, you are running, then the heart is beating in a regular way, which is the motion of a periodic Turnpike. And such periodic Turnpikes can be proved actually in this context, exactly with similar exponential estimates. Also, what we can prove is the situation of a partial Turnpike, like also the case of a runner. If you are a runner, so you can look at the curve of the speed of a runner. If the race is long enough, then what will do the runner? At the beginning, he will accelerate very much. Okay, this is the first phase, and then during a long time, the runner should run with during the most of the race, the speed should remain almost constant. So this is exactly the Turnpike, and maybe at the end, the runner will accelerate again in order to reach the final point. Okay, so this is what we call the partial Turnpike phenomenon. Okay, let me just give you a very brief flavor of how this property can be proved. It is quite easy actually, because as I told previously, the Turnpike, which is the steady state, is an equilibrium point of the Pontryagin extremals. So it means that you can linearize the Pontryagin equations near the steady state. And when you linearize the equations, then you obtain a linear system of this form, z dot equal mz. And the matrix M, which is written here, is a Hamiltonian matrix, which is not a surprise, of course, because if you linearize Hamiltonian equations at some equilibrium points, then you obtain a Hamiltonian matrix, of course. And the main property of the Hamiltonian matrix is the property that if you take every eigenvalue of this Hamiltonian matrix, mu, then automatically also minus mu, mu bar, and minus mu bar are also eigenvalues. Now, moreover, if you put some controllability conditions on the system in the form of Kalman condition or something like that, then you can easily prove that all eigenvalues have a non-zero real part. So now the main consequence of the Hamiltonian property is that the matrix M is hyperbolic. Hyperbolic. So what does it mean? It means that near the equilibrium, which is the turnpike, you have exactly the phase portrait of a saddle point. Meaning that you will start at some point, you will be maybe close to the separatrix, and you will spend much time exponentially small to the origin, which is the turnpike set. And then again, at the end, you will be close to the separatrix and go to the final point. So you see, it is a quite simple writing, and this gives you exactly the turnpike property with exponential estimates. It is not difficult. May it be in finite or in infinite dimension, by the way. It's the same proof. It's not difficult. So what I claim here is that the proof of the turnpike phenomenon is just a feature of a hyperbolicity phenomenon, and that's all. It's quite easy. Let me give some possible generalizations before going to the second part of my talk of the turnpike phenomenon, because there are many generalizations that have been considered by a number of authors who are cited here. And they are quite interesting because, for instance, there are some generalizations in terms of the Hamilton-Jacobi equations that are related to the notion of ergodicity of the value function solution of the Hamilton-Jacobi equation. There are quite, I will not comment more, but there are much weaker assumptions showing that in many situations you can expect to have the turnpike phenomenon. Maybe with a weaker turnpike property, like the one that is written here, which is weaker than the exponential turnpike. It is a measured turnpike property, which is also related to the famous notion of dissipativity that was introduced by Jan Willems in the 70s. So there is much literature about that, but I will not comment more. Just put some hints on that slide if you are interested. What I would like now to show you in the last part of the talk is the phenomenon of shape turnpike, which is the phenomenon of turnpike in a dynamical optimal design. And it was the main subject of the PhD of Gontran Lens, my PhD student. So let me show you the topic that we have given to him. Let us consider the optimal control problem that is written here, which is settled with PDE. And this PDE, as you can see, is the Dirichlet heat equation, but in which you put a source term in the form of the characteristic function of some subset, omega, which is varying in time. Okay, so key omega is equal to 1 whenever you are inside omega and 0 otherwise. Okay, so either 1 or 0. It is a source term that you put as a source term in the heat equation. And the optimal control problem that you consider is to minimize, let's say, the L2 norm, which is the discrepancy to some, let's say, to some target YD. And the control here, the control is the source term. So the control is a shape. The control is a subdomain. And the subdomains is any measurable subset of the domain capital omega in which you are considering the heat equation, which is, let's say, of a fixed Lebesgue measure. Okay, so the unknown, the control, is any measurable subset small omega of t of a fixed Lebesgue measure. This is our optimal control problem. And so what we have proved with Lance and Zoisois quite recently is that under some assumptions that I can also comment if you wish, we have the Turnpike phenomenon, which is the following. On the left, you can recover the optimal control problem that I have just showed you. Okay. On the right, we write the corresponding static optimal control problem, meaning that we are searching for omega, not depending on time, such that you have an equilibrium point of the dynamic. So meaning that you solve delta y plus q omega equals 0, you minimize the discrepancy to the target over all possible time-independent subset small omega of capital omega of a fixed Lebesgue measure. What we prove is that both problems have a unique solution. So on the left, the solution omega of t depends on time. On the right, the optimal solution does not depend on time because it is the steady state, it is static. And what we prove is that as you can expect actually, the discrepancy between the time-varying optimal control problem and the steady state, this discrepancy is small as capital T is going to the infinity. Here, more precisely, what we are able to prove, for instance, is that the average with respect to time of the optimal state is converging in L2 to y bar. And same thing for the average of the adjoint vector, same thing for the average of the characteristic function of the subset. Okay. And maybe how much time do I have, Diego? Maybe 4 or 5 minutes, something like that?
No, you have more. You have 12 minutes.
Okay, thank you very much. So in that case, I have time to show you the hint of how to prove that theorem. In order to prove a result on shape optimization, as you know, it is very usual to first convexify, relax the shape optimization problem. Because here, what is not good is that we deal with characteristic functions of subsets. But as you know, this class of unknowns does not enjoy any good compactness property. So if we convexify, if we make the so-called relaxation procedure in shape optimization, it means that we will enlarge the set of unknown, we convexify, and we replace, for instance, here, the characteristic function of omega with any L-infinite function a of x, which takes values between 0 and 1, and whose integral over the whole set capital omega is equal to the fixed Lebesgue measure that we have fixed before. And this is exactly the convexification in the L-infinite weak star topology. It is exactly that. So now that we have relaxed, that we have convexified, it means that on the left, you have the dynamical relaxed optimization problem, where the key omega has been replaced with a, the function a, and on the right, you have the static version. And now, in this form, we are exactly in the classical form of optimal control problems investigated, for instance, by Jacques-Louis Lyons a long time ago. It's a very, very classical setting now. And now it is completely obvious to state that in both cases, there exists unique optimal solutions. But it is, of course, not the end of the story, because what we would like to state is that the optimal solutions are characteristic function of some subset. So we would like the function A here, the optimal function A, to be almost everywhere equal to 0 or 1. We do not want that A be equal, for instance, to 1/2 over a subset. We want A to be the characteristic function of something. So in order to prove that, we derive first-order optimality conditions. So same thing as before, Pontryagin maximum principle on the left, Lagrange multiplier rule on the right. And in the case of this example, we see that we have to use the maximization condition of this first optimality condition, and by exploiting adequately this maximization condition and the bathtub principle, which is figured out here, we are able indeed generically, quotes, to imply, to show that indeed, for instance, here, the optimal solution A bar of X is equal to 1 whenever the adjoint lambda bar is beyond a threshold, and 0 otherwise. So now you see the idea in order to prove that A bar is the characteristic function of some subset is that the only bad situation that you would like to avoid absolutely is this one which is figured out here in red. This is the worst possible situation, because imagine that the adjoint vector lambda bar is a function that can be piecewise constant on some subset, with the constant being exactly equal to the threshold. This is what has to be avoided, because in that case, the bathtub principle does not imply that A bar takes either the value 1 or 0, but it can be any possible value. So it is exactly the situation to be avoided. And this is why we need anyway some assumptions in the theorem, just in order to avoid that situation. We want absolutely to avoid the situation where the adjoint would be constant, piecewise constant on a subset of positive measure. And that's all. And this is the only idea actually in this proof, in order to prove that we have a characteristic subset. Let me, let me switch the light on, because I cannot see, I now cannot see anything. Okay. Let me show you, to finish the talk, some numerical simulation. So here is a numerical simulation in 1D. So in 1D, we take the heat equation on the interval 0, 2, and here you have the time evolution of the optimal time varying subset. So you see that except around the beginning of the time interval and the end of the time interval, the optimal subset is essentially static. Essentially. And essentially, it consists of two connected components. Let me show you some videos also. So now here we are in 2D. We are in the square, capital omega equal to -1, 1 square. And you have here, vertically, you have the time evolution of the optimal subset, small omega of t. So again, you see that except near t equals 0 and near the final time, the the optimal shape, the optimal time varying shape, is essentially constant. Let me now show you the video, which is funny. So you can see here the time evolution. So it is between minus 0 and 1. So beginning, then we are along the turnpike, nothing happened. So you see, and again at the end, something happened. Beginning of the time interval, turnpike, nothing happens during a long time. And then at the end, something happens again. Okay. So, and you can see, by the way, on the numerical simulation that the topology of the set is changing, which is also not a surprise in some sense. Let me show you another geometry. So here here we changed the target YD. So let me show you the time evolution. So t equals 0, and then t equals 0, clack, time evolution. Then we are along the turnpike. Nothing happens during a long time. And again, around the end of the turnpike, a small evolution. So you can see again here that the topology of the optimal set is changing at the beginning. Okay, another configuration here. T equals 0, then we are along the turnpike, and towards the end of the time interval, things are evolving again. So you see the turnpike phenomenon is very visible again. The only non-trivial evolution is around t equals 0 and t equal capital T. And to finish, this is an example in 3D. So here we are in the cube 0, 1 to the 3. And so I will show you the time evolution of the optimal time evolving shape. So t equals 0. Then we are along the turnpike during a long time. And around capital T equal 1, there will be a time evolution again. Clack. Okay, let me maybe show you again. So the quality is not so good as before because it is in 3D, and as you can imagine, it is much more computationally demanding. Okay. Okay, and so let me conclude the talk by saying that here I have showed you the shape turnpike for linear PDE models. But for instance, what could be very interesting to investigate is to show the phenomenon of shape turnpike for general semi-linear PDE models, for instance, where when you add a semi-linearity like that, it could be also very much interesting to investigate nonlinear models that enjoy the maximum principal property, like the KDV or maybe the Saint-Venant equations, which would model the famous problem, you know, of trying to guess what can be the shape moving bottom pool wave generator, you know, that is illustrated on this picture. You know, this is you want to know what is the best shape moving at the bottom of the pool in order to produce a wave that could be optimal in order to make surf. And we expect there a turnpike phenomenon too. And this will be my conclusion. Thank you very much.
Thank you very much, Emmanuel, for this very beautiful talk. Now if anyone has some question, can open your microphone, or you can type the question here in the chat.
So please, I have a question, Diego.
Yes, Professor Vladimir Neves. Yes, you can.
Yes, it's okay. I could open also my video. Okay.
As you wish.
Okay, thank you, Emmanuel, for your talk. It's very nice. So you have talked about this type of control from OED, and your F could have some mean value, something like this, but certainly non-linear. And you showed us just linear PDs. And at the end of your talk, you talk about this exactly like conservation law, which is my domain. And I'd like to know a little bit more why you have just considered linear or at least semi-linear equations, in what is the main point to attack the conservation law, for instance? Thank you.
Thank you for your question, Vladimir. This is because I was a bit quick in describing the result. Let me come back to the how can I do? Sorry, let me stop sharing. No, let me. Can you see? No, you cannot see my screen now. Sorry. Okay, you can see it like that, I think. This is just to be able to switch. Okay, it is here at the beginning of at the introduction sorry, of the shaped Turnpike phenomenon. Actually, throughout the talk, I illustrated the shaped Turnpike phenomenon with the model of the Dirichlet heat equation. Okay, but actually what we have proved is a general result which is valid for any parabolic PDE, so a parabolic operator, which satisfies, this is our main assumption, I would say, which satisfies the maximum principle. Not the Pontryagin maximum principle, I mean, but the maximum principle for PDEs.
For the PDE, okay.
A comparison principle. And this is one of the main reasons why I think that we should also be able to prove something, for instance, on the KdV equation.
But for instance, you could start from conservation law, you could use a Venn-Scott's method, you parabolize, and so you have another parameter, but you could somehow try to change parameters, something like that, sends epsilon to 0 and get something to the conservation law. I'm just wondering.
I think that at least provided that on the equation that you consider you have a comparison principle, then I think something can be proved. I think something can be proved. Also, although of course you will have to deal with non-linearities, and in particular in the adjoint equations, but the main point, the main technical point, I would say, in the proof is really to play with comparison. Oh yeah, really, yes.
Okay, thank you so much. Nice.
You're welcome.
Nice to know.
Okay. Any other question or comment? There are many people. Congrats you. Emmanuel, for instance, for the case of system of PDEs, parabolic PDEs, so since you need some maximal principle, maybe, this is, I mean, as soon as the parabolic system satisfy maximal principle, you could adapt your argument to the case of system, right?
I think so.
There's no maximum for systems.
I don't have systems, indeed. No. I don't have systems. I have scalar PDEs.
Yes. Okay.
Yeah. I have scalar PDEs. Yeah.
And did you thought about system or?
Really not yet. Let me give you an argument showing you maybe what is what I could say is the second main difficulty. Mm-hmm. The second main difficulty I would say is there in the fact that the adjoint, when you look at the adjoint equation, okay, the adjoint state, the co-state may be constant on a subset of positive measure. This is the very bad situation where you can have what the people in shape optimization call the relaxation phenomenon, right? You would absolutely have to avoid that situation. How can you do that? The first idea that comes to mind is to be able to ensure that the solution lambda bar of the adjoint equation is analytic. Because if lambda bar were to be analytic, then of course it cannot be a constant on a subset of positive measure, right? Okay, so let us look at the system of PDEs, that is the first order optimality system. It does not seem so deep, okay, because you have here the equation for lambda bar, which depends on y bar. But the fact is that now our solution A bar here is something which is discontinuous, because you expect that A bar is either equal to 0 or to 1. And so you see that y bar is not at all analytic. At most, maybe it is analytic by parts or something like that. But you are not, you are leaving the analytic world, you see? And I would say that this is the second main difficulty. And if you investigate systems of PDEs, I imagine that this difficulty is even more sharp. I see.
Okay, thank you. Okay, thank you very much. Okay, any other question? No. So let us thanks again, Professor Emmanuel.
Thank you very much.
Now,
so Diego, sorry, I'm so sorry.
Oh,
but
sorry.
Let me tell you, I mean, for system parabolic equations, it's somehow difficult to obtain maximum principle. Somehow we have some invariant regions. You could see this from the book from Neste, okay? It's well written there for the second book of Neste. So somehow, since Emmanuel told us that one of the principles is to have a maximum principle for your equation, so scalar is okay, but this is not so easy. Mm-hmm. Sorry for interrupting you. Okay, I'm so sorry. I'm so sorry.
You are absolutely right, Vladimir. Absolutely right. Yeah.
Thank you. Thank you.
Okay, so thanks again, Vladimir and Emmanuel. And then the word now is with Juan. Okay, Juan.
Thank you, Diego, and thank you a lot, Professor Emmanuel Trelat, for your amazing talk.